informatics at the University of Edinburgh. He studies computational linguistics, artificial intelligence, and cognitive science. He is best known for putting forth combinatory category grammar, which relates syntax, semantic representation, information structure, and informational personality in a very completely transparent manner. This direct interface between the surface structure of a sentence and its underlying logical form is very important for cognitive scientists, because it reflects how a particular language is planned in the mind of a native speaker. Today, the title of his speech is Plans and the Predicate Argument Structure of Behavior. Please join me in welcoming Dr. Mark Steedman.
Thank you for inviting me and for that kind introduction. My title refers to a book which is getting quite old now, by Miller, Glanter and Prebrum, called Plans and the Structure of Behavior, which I read as an undergraduate and was so inspired by that I left psychology to work in artificial intelligence, because the one thing that was lacking in this book, which related practically all of intelligent behavior to an underlying planning system, the only thing that was lacking was a representation of a formal kind for plans themselves. And I'd heard that artificial intelligence people had some ideas about this, so I went and joined them, and that's partly why I'm here today. I'm using an unfamiliar computer because mine didn't work. That's computer science for you. Here's the outline. I'm going to talk briefly about planning as it is seen. Is this okay? In artificial intelligence. Then I'm going to talk about what relation the concepts that are used. The concepts that are used in artificial intelligence hold to natural language semantics. And that's a very complicated relation. I wish I could say that it was simpler. I'm then going to say more about natural language semantics under the heading of the general problem of representing content, the kind of content that I'm using to express myself in English at the moment, and in particular, the semantics that goes with content words rather than things like quantifiers. Then I'll talk very briefly at the end about how these two things can be put together and how we can hang language so directly onto human planning that we don't really have to talk about any separate evolution of language itself. Really, the much longer evolution of planning in vertebrates and particularly in primates is all that we need in order to explain the faculty. Okay, so I referred to the long tradition of work within psychology that relates complex behavior of all kinds, and in particular human language, to an underlying motor planning mechanism. And the evolution, which I don't have time to summarize here, is not only evolutionary, but it's also neurophysiological. The same parts of the brain are involved in... this is the only thing I'm going to say about the brain, by the way. The same parts of the brain are involved in motor planning and in the use of language, and it's also developmental. We can see certain connections between the abilities of children to solve plans like reaching round obstacles and their ability to use language. There's a regular progression in that that was first noted by Piaget. This raises the possibility that language is much more closely related to the rest of cognition than current linguistic theories of grammar would suggest. I'm going to argue, in fact, that practically every aspect of language is transparently connected to this underlying cognitive general purpose faculty. And I'm going to argue that our theories of cognition and of linguistics should be adjusted accordingly to bring them more into line. I'm going to talk in terms of planning as it's seen in robotics and AI. And I actually gave a talk here about 9 years ago on a similar, actually with a similar title, I suddenly realized a few days ago. And you can look on this as a progress report on the work that I've done since that talk, if any of you were there. The paper will sketch, and that's all I have time for, a path between representations. I can't read my slides up there. Representations at the level of a grounded sensory motor manifold of some kind, and on up to the level of language and parsing parser model learning. At the levels of planning and linguistic representation, there are two operations that you'll see recur. One is the operation of composition, which is formally represented. It's formally represented by the equation below. Composition is simply the application of a function f to the result of applying another function g to an argument x. And we'll also look at an operation of type raising, which turns arguments a into functions over functions f into the results of applying f to a. Crucially, human planning requires, this is actually all you need for animal planning, monkeys and bananas type planning. Human planning requires an additional element in the form of plan variables, which also is going to provide the basis for distinctively human language. If these operations are enough for animal planning, if one argued that they were enough for language, that would leave unexplained the fact that animals don't seem to have language. This is the additional element that is going to make everything work the way we see it work in human beings. But I'm getting ahead of the story, so let me... Okay. Apes really can solve the monkeys and bananas problem, so-called. It should be called the apes and bananas problem, but it isn't. And here is one of Curler's chimpanzees from the 20s, when he was interned, I think, on Mozambique or something like that, and had time to do this study. And this is a female chimpanzee called Grande, who is solving, the bananas are up here, and Grande is about to solve the monkeys and bananas problem by stacking up 4 crates, which is a pretty good solution to this problem. Apes, like chimpanzees, are very, very good at this kind of problem. They're very creative. They can solve them in multiple ways in response to whatever the environment makes available. What does Curler tell us about such planning? Curler tells us that such planning involves retrieving appropriate actions from memory. Yes, it works. Great. Yes, I'll use this. Okay, so the conclusion we can draw from these experiments is that such planning, animal planning, ape planning, involves retrieving appropriate actions. You can do an awful lot of things, and to plan you have to find some actions that you can do that will lead you towards the goal. And you also need to sequence such actions appropriately. And you need to do this in a way that has a reasonable chance of bringing about a desired state or goal, such as having the bananas. Incidentally, I was once giving a talk related to this, and someone said, oh, pigeons can do that, and directed me to a YouTube video of pigeons solving an apparently similar problem. But if you look at that video, you'll find that pigeons, which can't do this kind of planning, they can only do what's called reactive planning. Their behavior looks really quite different. This is quite different from brute force Skinnerian shaping. Curler showed very interestingly that in apes at least, such search has some rather constrained characteristics. It is object-oriented. That is, it depends on the presence of the tool. If the crates are there, the ape can come up with a solution. If the pole vaulting pole is there, then it can come up with a different solution. But if the crates aren't present, it can't make plans, or it has great difficulty in making plans, of the kind that involve going and getting some boxes and then piling them up. Even if it's been led to the experimental situation through a room, an adjacent room, that actually includes the boxes. They just really have great difficulty with that. Secondly, their planning appears to be forward chaining. That is, it works forward, breadth first, from the tools that are available in the situation to the goal, provided that that goal is reachable in a reasonably small number of steps, rather than backward chaining, in other words, working from goal to backwards to a plan that originates in the present situation. When I started as a graduate student, the dogma in AI was that planning was backward chaining and that you just couldn't do forward chaining planning. However, nowadays, all planners, all practical planners that actually work on the scale that we're talking about are actually forward chaining limited depth planners. It's a warning to us all that the deepest dogmas of our specializations can change underneath us. The first observation that this is an object-oriented process suggests that actions, such as piling up boxes and getting on them, are represented in memory associatively, that is, as properties of objects. This is what Gibson, in one of the most romantic ideas that is in play in cognitive science, called the affordances of objects. The second observation suggests that in the cruel and non-deterministic world that we live in, it's better to identify reasonably highly valued states that you have a chance of getting to than to optimize complete plans. In fact, it's only when you're at an advanced state of civilization where you've developed general purpose tools like credit cards, that you can which can do anything, that you can afford to backward chain from your desires to actual steps of the plan. And I'm going to come back for that, because that is at the heart of the crucial ingredient of human planning, which involves planning with variables. So I can make plans about telephone numbers, about calling people up with telephone numbers that I don't actually have access to in my head, but that I know ways of discovering. The problem of planning should therefore be viewed crucially as a problem of search. It's a search in what's called a Kripke model, which is simply the model that you would first think of, namely a lattice in which the nodes are states and the arcs connecting the nodes are the actions that are available in those states, if you like, the affordances of those states. A plan is a sequence of actions that culminates in a state that satisfies the goal of the plan. This means that search for plans is intrinsically recursive. So think of it as searching a tree. It's actually a lattice, but it's the same problem. It requires a push-down automaton to keep track of alternative paths to some limited depth. You don't want to examine the same action over and over again. You need to keep a track of how far down a list of possible actions you've got. And it's interesting in this connection that, as everybody in the room will know, a push-down automaton is also necessary to process recursive languages, which are the least complex class of languages that might have something to do with human languages. However, if monkeys can plan, and planning requires a PDA can't be enough for human language, because otherwise, why don't the apes have human language? There must be something more, and that's really what my talk is about. I'm going to skip over the next section. I've brought too many slides, as usual, and I want to make the point that all of the stuff that I'm talking about is actually implemented and works. So provided you have a representation of state that is sufficiently articulated, and it can't just be bits of pixels and joint angles, it has to be a propositional representation of some kind. If you have such a representation, then you can learn actions as what in AI are called strips rules. In other words, start states and end states specified in terms of preconditions for the action to be possible and changes to the state that result from it. If you have that, then you can do, with certain further heavy breathing, you can do the learning I'm talking about. And this is an example of learning from a real robot's action. So this is an errorful robot. The red curve is our learner iterating through training examples to its asymptote at about 73% correct prediction of the results of an errorful action. This is a noisy robot. In fact, it's very noisy. So often when it thinks it's putting something in a certain place, it's putting it in a different place. The interesting part of this is that if we do a traditional AI strips model, it doesn't do nearly as well because it doesn't model the error. Whereas our learner, given a fairly good state representation, will learn which actions will occur which way. I can talk further about this if anyone's interested. I know there are some robotics working on exactly this problem here in Ankara, here at METU. But let me pass on. How do we get from seriation and affordance, which is the two operations we've been looking at, where we see a bunch of crates and we associatively access the action of moving them to the right place and piling them on top of each other and climbing on them. And we seriate those actions into a plan. Well, seriation of actions is simply composition of finite state transducers that take one state description onto another one. And there are sensible ways of doing this, like strips and its descendants. And there are stupid ways of doing it, like exhaustively listing both of the states. You can do better than that. States are defined by the objects that they include. So what we're doing when the affordance of a state is a function from all those actions that are possible in that state into their respective result states. So getting you from here to here. And states are defined by the objects that they include. So this is like exchanging the objects for what's called a type-raised function that maps states into other states resulting from actions on those objects. So I see a crate and I map it into a function from the moving under the bananas function to the result of that, which is that it's at under the bananas or whatever my representation deals in. So I'm going to skip over this stuff fairly. It's rather obnoxiously notational. The affordance of a state, including a box, to an ape, is a function from actions like the box might fall, I might climb on the box, and I might put the box on another box, into the states that will result from those actions, which can be evaluated in that search through the tree or graph of possible states linked by actions. So for an ape, fall is an intransitive function from things to truth values, or if you like, other states. Climb on is a function from two things, the climber and the box, to another kind of state, and put on is a function from two boxes and an agent to some kind of state. The ape's concept of a box is therefore an object-oriented set of things that we might think of as the box falling, me climbing on the box, and me putting the box on another box. And all of those are things that we've described before. So planning is then the object-oriented seriation of affordances. And that means, so what we're saying is that the apes have this, because the apes can do this. So the only place for human planning to differ from animal planning is in a manner that supports language, in a manner that supports language, is in the event representation itself. There must be something in human event representation that means that we can make a kind of plan that other animals, including chimpanzees, which are as close as it gets, can't achieve. I'm going to come to what that ingredient is. You may be able to guess what it is, because Tomasello has sort of told us what it is in his musings on language acquisition. One of the striking differences between apes and us is ability to calculate on the basis of likely events in other people's minds. which is something that apes are also fairly limited at. But I want to make a digression before we get back to that point, which is really the conclusion of the talk, by saying a bit more about this action representation, and in particular, in what sense we can ground it in experience in the world. We can't ground it directly. Any of you who have tried to exploit the fact that robots exist in the world and tried to do anything with robots' native representation of the world as joint angles and pixels and haptic signals of various kinds will know that you can't do anything at that level. You need a higher level representation. And the higher level representation is very ramified. So even a box falling is a combination of features like the appearance of looming that tells you that this is what's about to happen, and the consequences like your experience of being hurt by this event, and so on. In fact, the very ramified nature of this dynamic event knowledge that we all have and that we share with apes is actually one reason that languages can vary in the way they carve the conceptual representation at the joints. If I have time, I will have an example from Turkish later on that I just ran across in preparing this talk. But it's well known that expressions in one language very frequently don't translate directly into expressions in the other one. So a familiar one from the machine translation field is that in English you can use run causatively in expressions like run across the road, but in French you can't do that. You just can't say run across the road in so many words. You have to say cross the road at a run or by running, something like that. And this is what makes machine translation very difficult. So to understand the connection between planning of the kind that we've just been talking about in Scripps terms and semantics of the kind that's involved in natural language, we need to better understand the grounded event representation. So let me digress on that for a bit before returning to the link between planning. Linguists and the artificial intelligence here, people like Roger Schank, linguists like Chuck Fillmore, have for years tried to define the semantics that would be truly cross-linguistic. But they've partly done that for reasons of wanting to do machine translation, but also for the sheer linguistic interest in it. So since the very literal representations of Montague, these are all the ways that people have proposed to talk about the sentence, bugs kill plants. Sorry, I'm off the microphone. These are all the ways that people have tried to talk about the sentence bugs kills plants. So for Montague, kill just meant kill prime. Because he was really interested in the quantifiers and then operators like negation. But Macaulay proposed articulating the lexical entry for kill in such a way as to make the logical form for bugs kill plants to be this thing, this causative thing, with an explicit causative primitive in it. Doughty, at about the same time, proposed a different version, this notation here. Talmy produced one of my favorite ones, bugs are the author of plants result to die. Van Valen did another one. My current favorite is Cliff Goddard's bugs do something to plants, and because of this, something happens to plants at the same time, and because of this, something happens to plants' body, and because of this, after this, plants are not living anymore. The whole thing is actually reminiscent of a thing that was called Basic English, invented by Ogden. I guess my batteries go. And it gives one a feeling that it's not getting anywhere. If there are so many ways of thinking about this, and really you only have to look at this example to see that none of them really work as soon as you look at a different example. Do plants have a body? I'm not sure. What this cries out for is machine learning. So can we learn this automatically using some kind of machine learning where the primitives are the hidden variables that we're trying to drag out of the data? I'm going to briefly argue that we can do this. There are two approaches to this problem. So the thing that we're going to do is we're going to take the parsers that we have managed to develop over the time, largely since I last talked here. We're going to run them over large amounts of text on the web, and we're going to we're going to find correlations between ways of saying things. The real problem in question answering on the web is not that the information isn't there. It's that the information is expressed in a way that is not obvious from your question. You asked about the author of Macbeth, and the text talks about Shakespeare's Macbeth. It's not obvious how those two things are connected. There are two approaches to this idea of dragging it out of text. One is clustering by collocation, which is an idea that goes back to latent semantic analysis in the 90s, but has recently been taken up by all of these people here. And this is where we represent the meaning of a word by a vector, maybe a compressed vector, representing its collocations, the content word collocations that it occurs with, so that words like dog occur in similar collocations through the text as cat. So we think that they are similar in meaning. The advantage of this approach is we can do composition via linear algebraic operations, like vector multiplication. We've got vectors, we've got lemons, we like lemonade, we've got vectors, we'll multiply them, or add them. It's a very good method for under-specifying meanings, because if you've got an ambiguous word like bank, its vector representation is the superposition of its two meanings, and if you intersect it with another word like money, it'll actually disambiguate it. But there are problems with this approach that I won't go into. There's an alternative, which is to cluster by denotation, which has also been pursued over a number of years, and which I'm pursuing myself with my student, ex-student now, Mike Lewis, where we use a different representation, which I'm going to tell you about briefly, which has the advantage that we can do composition via traditional logical operators like negation. The problem with vectors is, how do you negate a vector? The inverse of the vector is not going to give you a very good answer to that. And the advantage of keeping composition to traditional logical operators is that it's then good for doing inference. And if there's one thing that I have learned about semantics, it's that the only thing that matters about semantics is that it supports inference efficiently. We must distinguish paraphrase from entailment in doing what I'm going to put before you. So if we read text with our parser, even if our parser is not very good, we should be able to work out that when we hear somebody of type politician being elected to something of type office, like Obama being elected president, we also often read that that same person ran for that office, perhaps at a slightly different time. But the reverse doesn't hold. Most people who run for office are never heard of again. They certainly don't get elected to that office. And what that means is that this is not a paraphrase because it's directional. And detecting true paraphrases, which are interesting because that's the relation between Shakespeare, who was the author of Macbeth, and Shakespeare's Macbeth. These rely on global properties of the named entity relation graph. So we can read the text, we can drag out all the statements about recognizable people like Obama, and we can put them into a big graph. So we have all the relations that are stated of Obama, provided we can decide which Obama we're talking about in a single graph. We're using here a technique that we borrowed from Jonathan Berrand. What we find if we read the text automatically is that, for instance, if we're looking at named entities that are countries, we find that if a country conquered another country, then we also read that it invades. And we get a 0.9% probability on that relation. It's highly predictive. We also find that if a country invaded another one, we also read that they attack. That's a slightly lower probability. And we also read that if someone conquered one country conquered another one, then they also attack. But actually, although it's probably true, we actually find it with low probability. We also find that if a country bombs another, it also attacks with high probability. Now, what we have to do is decide which of these probabilities are genuine entailments. In other words, we can treat them as certainties or near certainties, and which of them are noise. That it just happened to be by accident that we read about. It's just a coincidence that these two things co-occur. There's a technique called linear integer programming, which is precisely for relaxing a graph of continuous probabilities like this into something like a binary entailment graph. So what we do is we take advantage of the fact that a graph of entailments must be closed under transitivity. So if A entails B and B entails C, then A has to entail C. And that's how we deal with the low probability of whatever it was, conquering, entailing, attacking. Because when we apply linear programming to that graph, the graph that's implicit in the probabilities that I talked about, we will get this cleaner graph here, in which this probability here has been promoted to certainty by the entailment closure. Now, whenever in this graph we find expressions relating the same things, all mutually pointing to each other. In other words, whenever there's a clique within this graph, we can collapse the clique to a single cluster. We can just call it relation 39, because it's the common meaning of x invaded y and invasion of x by y. Wrong way around. Right way around. Okay, I hope that that's clear and that people will have taken that as far as at the level that I've been able to present it. So what we can now do is we can make a lexicon for our parser that will redefine the meaning of attack in terms of the cluster of paraphrases of attack, whatever those are, and I call that relation 1 here, and it holds between two entities, two countries, and there's a Davidsonian event variable here. Bombing is a relation that includes the attack relation 1, but also the distinctively bombing cluster 4. Invading is a different conjunction of the attacking cluster and the distinctively invading cluster, while conquer and annex are the conjunction of attacking, invading, and the cluster 3, which is distinctive to both conquering and annexing. So what we've now done is we've blown up we've got something more sophisticated than Montague's conquer prime. We've got a conjunction of things that all have to be true. And the advantage, if it's true that a country A invaded, conquered a country B. Now, the important thing about this is that these logical forms support correct inference under negation, such as that conquered entails attacked, but didn't invade entails didn't conquer. So if this conjunction here, if this conjunct here is false, then that's enough to tell you that the whole conjunction is false. So to answer a question, did X invade Y, we look for sentences which subsume the conjunctive logical form 2 and 1, or satisfy its negation, not 2 or not 1. I'll skip the next bullet because
more relations.
I'm sorry?
What's happening if instead of 2 in the n relations, how do we do that?
You just have a big conjunction. And in fact, if you look at our, I haven't brought an actual example here, but some of my graphs are long conjunctions. But that's okay, because your question was, did X conquer Y? And you've got the advantage that you immediately know what crucial properties are. And you know things like that if only one of them is false, then that's enough to tell you the whole thing is false. And what we're doing, well, I'm going to make some remarks about what we're doing in a second. I'll just say one more about this. If we do our machine reading cross-linguistically, which we have done, then we'll see that some of these, first of all, we'll be able to collect the French way of talking about the relation between Shakespeare and Macbeth, because we can identify those named entities as being the same as in the English relation. And if you look at the cross-linguistic clusters that we get out of this, then what you find is that some of the elements in the cluster correspond to exactly the kind of primitives that Macaulay and the rest of them were looking for in the 70s. Others are more arcane. Some of them are surprising. You didn't think that there was a primitive that underlay these two expressions, but your machine learning is telling you that is the case. Again, all of this works. These are some numbers that shows that it works a bit better than the vector-based semantics, but they're just numbers. I mean, they just show that we actually do know what we're talking about and we can make it work at the scale of the World Wide Web. So I'm going to pass over that just as a placeholder. I want to make a few brief philosophical reflections which go back to my status as one of Maggie's very early undergraduates when she taught me about some of this stuff and gave me a long lifetime interest in it. Our hidden relations like relation 1, 2, and 3 resemble what are called meaning postulates, which are a thing postulated by Carnap, who wanted them in support of his development of inductive logic and probability, basically to keep the model small and consistent. So he didn't want to represent in his model the fact that if somebody is both a bachelor and unmarried and male. He said you have a meaning postulate that says all you need to say is that they're a bachelor, and then that entails that they are both unmarried and male. And this suggests that our semantic representation that we're dragging out of machine reading of this text expresses what you might think of as a pragmatic empiricist view of analytic meaning, of the kind advocated by Quine. Quine said that existing notions of analytic meaning were meaningless because you couldn't say where analytic meaning, that's necessary meaning that follows from the way the world works, began and inference took, and specific knowledge took over. Even more wildly and more romantically, it can also be viewed as a statistical and text-based approach to treating meaning as use. We're treating the text on the web as our source, and that's use, and we're dragging this information out of it, not by thinking about it in our armchairs, but by using machine learning. And that's intended to provoke the philosophers in the audience. So let me move into the last section of the talk. How am I doing for time? Okay, that's good. I'm going to make one more grand skip where I leave something out. That'll be okay. Okay, we've seen that partially searching the plan graph is an intrinsically recursive process. So we said that we needed at least a push-down automaton to keep track of it. And we might ask at this point whether a push-down automaton is enough. In fact, we might suspect that it's not enough, because the apes must have that much. And yet, there are limitations on the apes' planning. The answer to the question of whether a PDA is enough is that it depends on the class of plans that you want to make. In particular, if your set of plan types, so you can think of a plan as a function from a certain number of entities to getting to a result, okay? If your set of plan types is unbounded, so for instance, if you can have plans that involve arbitrarily many entities, then a push-down automaton is not going to be enough. And I'm going to say briefly why that is, but for those of you who know this kind of thing, it's the same reason that a push-down automaton is not enough for a phrase-structured grammar if the phrase-structured grammar has unboundedly many non-terminals. Instead of just having VP, NP, N, and a few others, it's got an unbounded number of types of non-terminals. Collaborative plans of the kind that human beings are very, very good at, and apes are really hopeless at. These are exemplified by examples like finding somebody to help me mind the baby. Okay, everybody knows how to mind a baby, but you very often need help to mind the baby. So you may also need to, your plan may be to find somebody to promise to help to mind the baby. Or, in fact, we can recurse unboundedly, so we can find somebody to ask to promise to help to mind the baby. We can clearly go on doing this unboundedly. Maybe this is not maybe there's something wrong with this example. Anyway, searching a graph with unboundedly many node types needs a thing called an embedded pushdown automaton, in which the stack of the pushdown automaton can include stack-valued elements. And this suggests that collaborative planning with other minds provides not only the only known motivation for language. You know, Tomasello has made the point that that's why children learn language, for the interpersonal interaction. But it also provides the characteristic automaton that supports its use. And to see that that is the case, we should look at the grammar of sentences such as to and find out what automata theoretic power we need to handle that. Because that is not a problematic aspect of natural language we can do. This is the part I'm going to skip. As the introduction very kindly said, I've been known for some years for very perversely developing an alternative to the transformationalist theory of linguistic structure, which has the property of eliminating move. I've always disliked move as a computationalist because I didn't like that. The metaphor loses its appeal when you're actually implementing a program. And this is a thing called combinatory categorical grammar. And in combinatory categorical grammar, we have lexical items, which are the only language-specific information. So this is the transitive verb met, and it says it's something that wants a noun phrase to its right, like met Harry, and to yield something which wants a noun phrase to its left, meaning, like, for instance, Harry, to end up meaning Harry met Sally, or the other way around, I think I said it. And that's the syntactic projection from these lexical entries onto sentences crucially depends on the two operations that we've seen in the planner of type raising, exchanging the role of functions and arguments, and composition, forming new functions by composing the ones that are there in the lexicon. I'll pass over the comparison with Turkish transitive verbs, except to say that if you want to specify Turkish, all you have to do for the same meaning is to reverse the direction of this slash, since Turkish is verb final. I'll say no more about that example, although we could come back to it. In this framework, and this is the most controversial part of the framework, all arguments are type raised as if they had case, as if English, even English, were a sensible language like Turkish that had unambiguous case or relatively unambiguous case marking on all its noun phrases. So you're going to see that the simplest noun phrases, even like Harry, are type raised. In fact, they have nominative type raised categories, accusative type raised categories, which say they have to behave as objects, and so on. And what this means is that in English transfers the work that Turkish does with inflectional morphology into the parsing model. The parsing model has to build a model that says, well, if there's a verb to your right, you're probably nominative. And that's the way English gets away without morphological case. I'm going to pass over the fact that this is a formalism that couples syntactic and semantic derivation totally, that it has been used to explain the kind of things that have induced rules of movement, like the relative clause construction, where this is entirely handled by the nominative, composing categories like the nominative Harry and the transitive verb. Its most spectacular success is in coordination, where it immediately predicts that you would actually have to stop a language like English, treating things like Sally a record as conjoinable constituents, typable constituents. And that's actually the most interesting, one of the most interesting parts of the theory. The important thing for our purpose is that CCG is beyond context-free. It's what's called near context-free. It's actually the lowest, it's the least expressive formalism that is greater, is more expressive, strictly more expressive than context-free grammar. And this is because the combination of type raising and generalized composition sort of is a sweet spot in terms of the kind of permuting and rebracketing that you find in natural grammars, and that transformations were invented to to capture. CCG and its close relative tree adjoining grammar are provably weakly equivalent to a thing called linear index grammar, which you don't need to know about. But it's from that proof that we know that they are not merely mildly context sensitive, but nearly context free. And in fact, maybe one of the most important things, if you don't know it already, is that there are many more levels to the Chomsky hierarchy than type 1, type 2, and type 3 that you're familiar with. And just above type 2 is what you might think of as type 1.9 recurring, which is this class of languages that includes tree adjoining languages and combinatory categorial languages. And these are strictly, this is just the Chomsky hierarchy extended. If I had time, I would take you through the fact that if we look at the construction, I would take you through the way in which the operations of type raising, these are type raised categories, these are verb categories. The operation of composition and the type raising abbreviated here as Akara give us these verb clusters. So in varieties of German, such as the variety spoken in Zurich, the sentence that comes out is that we helped Hans paint the house comes out as that we, Hans, the house, helped paint. And the way this is analyzed, so the paint needs the house and the help needs the hands, so the dependencies cross. So this is not context free. And it's the operation of composition, specifically cross-composition, that allows you to compose these functions into a sort of composite helped paint. Here's a more complicated example of the same thing. The equivalent of we let the children help Hans paint the house comes up with 3 nested dependencies and the verb cluster on the right. The thing that we could just note in passing is that if we look at clusters like this verb cluster here, it's a function with arbitrarily many arguments. So we can go on stacking up these verbs like help and hear and see as long as we like, and make more and more cross dependencies in this construction. So what we're saying here is that this part of the grammar of this variety of Dutch, it actually creates constituents that are homologous to the collaborative plans that we looked at earlier, like find someone to let someone help someone do something. And that's really the core of the argument that these two things are the same. So I'm going to give a rather lengthy... What's my time? Yeah, I'll wrap up with 2 slides. 3 slides. What this shows is that we can treat the lexicon as the only locus of language-specific information in the grammar. The universal projective syntactic component is then language-independent and construction-free, and mainly consists of various forms of the combinators compose and type-raised T. In evolutionary terms, we can think of these combinators, or at least the base forms of these combinators, as being provided ready-made by a sensory motor planning mechanism, most of which we share with a number of animals. We certainly share all of this stuff with apes, and probably with some more surprising animals than that. The problem of parsing natural language grammars of this extended class that I just identified in the Chomsky hierarchy is automata theoretically equivalent to the problem of planning for cooperation with other minds. And that's the thing that the apes are bad at, and that you need in order to generate a mechanism of this power to bring about both of these abilities, which seem unique to humans. The ability to plan with other actors in mind, and the ability to entertain plans with arbitrary numbers. The other faculties of this language. We can think of this as as reflecting the following stages of the following evolutionary stages. And I don't usually talk about evolution, but I'm just going to risk it just this once. Long ago, long before there were mammals, we find reactive planning with non-recursive knowledge representations. In other words, finite state probabilistic planning. Pigeons can certainly do it, and if pigeons can do it, I'm sure dinosaurs could do it. It doesn't get you very far. It enables you to be a pigeon, but that's not so great. The next stage is forward chaining, breadth first, deliberative planning with non-recursive knowledge representation, still, so not truly recursive, so embedding, so that you can have plans made up of plans made up of actions, but not plans that call themselves as arguments in a truly recursive fashion. And these require composition to put them together, type raising to associate them with objects, and a simulated push-down automaton to do the search. When I talk about a push-down automaton, I'm always talking about something that's being simulated by a finite state machine. And that's one reason why I think that Maggie Bowden's pessimism about identifying precise, these computational mechanisms with directly localized function in the brain is difficult, because there are many ways of simulating a push-down automaton to some limited degree of approximation. Now that push-down automaton also supports recursive concepts in the knowledge representation, which animals actually don't show very much evidence of. But a push-down automata alone is not enough to support human planning and human language, which the other animals lack. And the reason it's not enough is because to make the kind of plans that we make, we need to plan with information increasing actions. So if I want to phone my brother up, I don't remember his phone number, but I know how to get hold of it. So I can make a plan which says, find out the number and call that number. Now, I used to do it with a phone book, but now I do it with I just look on my phone, so it's a rather trivial plan. That's what's called a plan variable. The number is a variable x, where my plan is find what the value of x is and then call that value. The business of gathering information and cooperative action from other human beings is very similar. It's an information increasing activity. If we do that, then we are likely, if we're thinking about reasonably complicated cooperations like that are necessary for successful child rearing, and I'm thinking of a very interesting book by Hardy from a few years back, who argues that this is where this planning comes from. You have plans which have unboundedly many plan variables. Plan variables, things like the phone book or the phone number, but also plan variables like someone who will do this thing for me. This gets you, in order to plan with these things, you need a more complicated automaton, the embedded push-down automaton. This is a device which still has a single stack, but where the values on the stack can be stack valued. And that's all you need to do the two things that we're talking about. Planning with multiple agents. And once you have this, it immediately supports near contracts-free natural language grammar, as attested by languages like English, Turkish, and the German example that I looked at. Now, the interesting point about this, with which I will conclude, is that this last step will happen without any further evolutionary work. You might need to do a little tuning of the vocal tract, and there is evidence of evolution of our vocal tract for vocal language. But even before you have vocal language, you will be able to do some kind of language, maybe a sign language of some kind, without any further evolutionary work. And I think that is important, because the one thing that we're certain about language is that it did evolve, if it evolved at all, incredibly quickly. It just seems to be not there at one point, and not there in our closest relatives who survived from that point, but instantaneously with us thereafter. So I'm going to stop at that point and ask for questions.
Okay. I have questions, but I'm going to resist the temptation to go last.
Yeah. My question is about this conjunctive lexical categories. When it comes to obtain entailments from a negation, a conjunction does not seem to pay off very well, because if I have a lexical category with a semantics like P and Q and R, if I know that the verb is negated, then I cannot entail many very useful things because I obtain a disjunction of the negations of the conjunct. So my question is this conjunctive, being the lexical categories, conjunctive is a design feature, or is it possible to obtain disjunctive categories I especially make use of when I have a negation, so that if I have a disjunctive, if I could have a disjunctive lexical category, then the negation immediately gives me n number of entailments where n is the number of disjunctions. So that's my question.
Okay, I don't know whether I'll be able to find the slide. First of all, I would contest the idea that conjunction is not it may be that some of the meanings that we're looking for are not merely conjunctive. That's an open probability. But I would, possibility. I would contest the idea that this is not the reading that we want. This behaves very well with negation. Now, in language, there's more to say about negation than logical negation and semantics. There's a notion of polarity that I have actually written a whole book getting into this form of grammar. But if we abstract away from that degree of complication, so we admit that negation in language does have some special features. The basic conjunctive meaning of invade as relation 2 and relation 1 is just what we want for negation. Because first of all, to decide whether X did or did not invade Y, we want to either satisfy both conjuncts. Now, remember that all ways of saying invade will be paraphrases. So for all of them, we've crawled the web and we've made them all mean this conjunctive thing. Okay. So either we'll find that there's another way of saying that conjunction, or when we negate it and move negation in past the conjunction, then we get not rel 2 or not.
Okay, if you
find either of those, then the noun is false. So it's exactly what we need to do entailment fast and efficiently, rather than pushing it out into the logic. If you push it into the logic with literal Carnapian meaning postulates, what happens is it's perfectly good logic, but you never hear back from your theorem prover because it gets lost in that version of search.
Yeah, I was thinking that negation was had a global scope over all the conjunction, but if you really can pin down, I think thank you.
Duygu? You need the mic.
Question. So when you say the difference between animal planning and human planning, you said it's the event representation that differs. I'm just trying to reconstruct it from the perspective of forward chaining. So they are able to use the available tools, using the affordances from tool to the aim, and that somehow indicates that they are able to construct their event representations.
Right.
But they are not able to construct event representations of others. In a way, can I replace this with...
Yes, although I think there's a more general way of stating it than you've stated it. What they're bad at is planning that involves unknowns. So any kind of plan that involves, if I had a box, then I could do this, is very difficult for them. And I think that the two go together. I think that planning with other minds is simply another way of planning with unknowns. And this is the crucial one.
Can I replace that planning with unknowns with prediction as well? So, because it's a kind of planning with unknowns. Can I think of prediction as planning the unknown?
I think all planning involves prediction, and that if we agree that we're dealing with these two slightly different versions of planning, I think that they both involve prediction. And the thing that the apes are bad at is making predictions about other people.
Thanks ever so much, Mark. Just two things. I absolutely agree about that book, Milligalanta Prebrum, a wonderful book. Turned me onto this stuff too. My question is, right at the end, you talked about our language, to have evolved our language. We needed a particular change in the vocal tract.
Yeah.
What do you mean by that? I don't just mean what was it, but I mean, well, why? Why was that necessary?
So I think that vocal language has advantages of sort of speaking around, communicating around obstacles and corners and stuff like that. The evidence that that we have rather rapidly evolved to do that because presumably of some advantage over sign language, which doesn't have that property, is that our vocal tract is actually rather badly designed for it's rather bad for all the other things it has to do. So we are not only the only animal that has language, we're also the only animal that can choke on its own food. So for most animals, including the chimpanzees, who really can't vocalize in the necessary way at all, it's just impossible for them. They have to either be breathing or they have to be eating, and the two pathways are completely isolated from one another. So it's only human beings who need the Heimlich maneuver performed on them, because they may actually do some speaking while they're eating and stuff like that. So that's the evidence that there was a little bit of evolution once we already had this something very like a language for communicating with, some optimization to apply it with vocal language. So that's what I meant anyway, about a tiny bit of fiddling with the larynx.
Any questions?
So this universal language of thought that allows us to learn all these things in language is essentially unavailable after a certain period in a direct sense. It's only through language that we sort of self-supervise the meanings. Can we say the same thing about plans? The kind of daily plans that we make and the kind of...
Yes, and I think that is why the project to actually take advantage of the fact that robots exist in the world and actually have a sensory motor manifold of some kind, the attempt to actually use that to support cognition, to support planning, and to support language has, I think, it's been a lot harder than we thought it was going to be. I don't think we've done very well at that project, because as we found when we were doing the learning of strips actions that I very briefly alluded to early in the talk, what we found was that we had to provide a language that was applicable at the level of the strips and compile it into machine primitives of the kind that the robot could understand. And that was so painful that, in fact, I could tell you a funny story about the robot, but I won't start on it. I think it actually underlines a limitation on the attempt that I've outlined to mine that information from text, because there are things that are so banal that you will never find them mentioned in text. So one of the things that we found that we hadn't mined was the fact that anything can only be, I'm having trouble with quantifiers. Nothing can be in more than one place at the same time. Okay. Now that's the kind of thing that probably pigeons know, certainly cats know, and it's part of the animal cognition that took millions of years, 500 million years to evolve. I don't think that we're going to find that from text. And it was exactly that kind of thing that we found that either we built into the low-level state representation, so it actually happened to be the case that the way we represented location was by kind of closed world assumption. So if we said something was in a place, that meant that it wasn't in any other place. In that case, we were lucky, but I think there's an awful lot of knowledge that is embedded in that low-level representation that we share with cats that it is very difficult for us to discover indeed. It's deeper than anything that's represented in the languages of the world. And I think that we'll have to simulate it, we'll have to specify it by hand. What we won't have to specify is the fact that kill means cause to die. We can actually work that out from the text. Up in the front. On the balcony.
Thank you, first of all, for the nice talk. My question was about actually the entailment, so it's a nice coincidence that it's up there. So my question was that is this conjunctions, are these conjunctions cancelable, or if it means that you can cancel any of the conjuncts, that you shouldn't be reducing them to a single point in the graph. For example, I don't know if it makes sense in English, but in Turkish I can say the equivalent of x and x, y, even without attacking. So if I can say this, does that mean I'm cancelling the conjunction, or does this mean that it was wrong for example, the Turkish equivalent to reduce them to a single point in the graph?
That's a very good question. These things that I could have gone on a long list on what these things correspond to in familiar philosophical and linguistic approaches. And one of the other ideas that I could have invoked here is the idea of a default. So these are actually defaults. It's not actually the case that everybody who is talked of as invading a place attacked it. There are a few exceptions. So in the Glorious Revolution of 1688 in Britain, William of Orange was said to invade the country, but actually he was invited in and nobody put up a fight. So he didn't actually attack, he just sort of made a show of it. And in that sense, these are defaults and they're cancelable. What the mechanism for cancelling is, I don't know. In fact, default logic is a wonderful idea whose practice is very, very difficult to take advantage of. So I would like to say that these are things that will be strong enough to actually get you through the reasoning most of the time. But another thing that they're like is what are they called? Prototypes, where there are actually degrees to which individual instances of events conform to this recipe. And that may well involve a way of dealing with the occasion when the default is incorrect. There's another idea floating around, which is the idea of presupposition, where a contrast is drawn between true presuppositions and cancelable presuppositions. I would think that the cancelable presuppositions ought to come under this same heading of default. But it's an unexplored area. At the moment, we're very happy if we can do better on question answering than the competition by exploiting these entailments. But of course, we make errors.
Your conclusion or your argument, can I summarize it as follows? Language, especially its syntax, and planning share a common mechanism, cognitive mechanism, which can be implemented by a push-down automaton, embedded push-down automaton. And your conclusion, the last conclusion was that what we need to jump to language from planning was the necessary or sufficient development of the vocal tract. But are we not missing another important aspect about language, which is symbolization? Because it seems that in planning, we seem to have at most kind of iconic kind of symbolization, because the events that we have to represent in our minds should be somehow analogous to the environment. But language seems to be very different because it also involves a level of arbitrary symbolization. So what do you think about the difference between these possible two types of representation? Representing events versus representing words.
Right, so I think that both kinds of planning, the animal planning, which does not involve variables and agents and things like that, and other minds, and human planning, which does involve those things, I think that both of those are symbolic. In fact, what we found in making a learner for the actions from robot data was that you had to have a symbolic representation. There just isn't a way of moving directly from the low-level joint angle representation to the high level that you need for planning. You have to make it symbolic, just as in interpreting a picture, you can't do it as an object. You can't do it at the level of the pixel. You have to have some kind of features that are independent of position and orientation or whatever your invariants are. So all of the stuff that I'm talking about demands symbolization. The crucial evolutionary step is really being able to plan with variables, being able to make a plan to use a phone number whose identity you don't yet know. Because the alternative is, well, either I'll dial 1, or I'll dial 2, or I'll dial 3, or I'll dial... And that is not a good plan. So it's that new level of still symbolic programming, planning, that takes you into the domain where you can support language. Now, it is nothing to do with the evolution of the vocal tract. The progression from animal planning to human planning is nothing to do with the vocal tract. The vocal tract is an afterthought. If you have language of a sort of grunts and waving your arms kind and pointing, probably something as fully articulated as modern sign language, then there is an advantage to doing it with a voice because you can do it over distance and around obstacles. And that's the pressure when we already had everything that we needed for language, and including language. It's that pressure that means that our vocal tracts show the same kind of hasty evolution as our upright posture. Our backs are also rather badly designed. I really stress that the evolution of the vocal tract is an afterthought. It's not the precondition, as Tecumseh Fitch and various more animal-oriented people would have us believe.
Okay, if there are no more questions, I think... Thank you, Mark.
Thank you.